So what happened here? First of all, the problem is this returns uninitialized memory. Okay. So what we're summing up here is we're summing up a bunch of uninitialized values. Okay. A of I is uninitialized. Sum therefore here is in essence an uninitialized value. But Valgrind doesn't report it at this point. Why? Because we're just passing this value along. Right? Nothing in the outcome of the computation that's visible to the user so far depends on it. Only at this point where we take the return value do we output it. By the way, you said that's probably summary right, of course, as well, right? Sum is not only summing up uninitialized values, it is itself uninitialized as well. It should be that, so it doesn't change this yet. So if I I'm getting the same output. So Valgrind is pretty smart here, right? Even though it realized up here that we were accessing uninitialized memory, okay, it didn't complain until down here when we actually tried to do something that has a side effect, such as reporting this result to the user. Okay, so what else does Valgrind do? Valgrind can report out-of-bound accesses. I mentioned that, and out-of-bound is of course both to the left as well as to the right. So for instance, if I say s plus equal a of -1, and I do that, I'm getting the error message that says invalid read of size 4. The address is 4 bytes before a block of size 40 was added in here. By the way, block of size 40 alloc, of course, is this array of ints, 10 ints times 4, 40 bytes.
What if you have the memory before the array?
What if I have the memory before the array? Okay, that's a good question. So let me explain. I have another example and then maybe answering that question. Okay. Which comes next. Okay. So what if, for instance, let's say I have I allocate a second array, okay, with 10 bytes, and but then of course I can write something to that second array, can output it, and let's say I'm accessing that second array through a pointer of the first array. So to be clear, what I'm doing here is I'm setting the first element of this array to 5. Outputting it, outputs 5, nothing big here. Then I am computing the pointer distance between B and A, and I'm setting A with a of I, which is the pointer distance to 2, that overrides the value of B of 0. I'm outputting it. So just to show you this, if I run this program, I'm seeing 5 and then 2, right? So here 5, outputting B of 0. I'm setting it to 2, I'm using the pointer to A, right? So this is, as far as A is concerned, this is an out-of-bounds access. But the value is 2, and the question is, does Valgrind detect it? Anyone want to guess? Valgrind does not. It says 0 errors. Okay. So to answer your question, if the memory that is before is part of a correctly allocated section, Valgrind will not flag an error. Valgrind just looks at, has that memory been properly allocated, and also has it been initialized? Has it been written to before it's being read from? What Valgrind does internally, or what I should say, what the memcheck skin does, it keeps track of a map, a bit map, that records the state of every single bit in memory, a bit, not byte, and records whether it's been allocated or been written to or not. Or more specifically, whether it's been read from before it has been written to. Okay. Now,
your example, can you bring your example back up?
Yeah.
It looks like that will be detected sometimes, but not other times. When you've got your new, it just happens to be that those are close enough that your subtraction gives you an address, right?
No, actually, this is by design, right? I mean, I'm setting I to B minus A.
Right, so-
The C standard guarantees that this refers to B of 0.
Right, but B is, you're allocating off your heap up there from the array.
Yeah.
And so you're allocating 2 arrays, and they happen to be,
No, so let me say what happened in such a case. So what Valgrind actually does is it provides its own runtime library. Okay. And so you're not using the malloc version that comes with libc. In fact, you're seeing, if you looked at the output, you see this, there's here. Somewhere we had a backtrace. Yeah, here it says, look, it says allocated by operator new in a file called VG for Valgrind replace malloc. The Valgrind allocator, the memory allocator, is such that it allocates large amounts of, relatively large amounts of memory next to each item. So those are fences. So it can detect overflows as long as they are within this range. Because it knows that this is a red zone, it's a buffer space.
so it doesn't fence each allocation, it fences groups of allocation?
No, each allocation is being fenced. Each allocation. And by default, like for instance, if you do a minimum size allocations, the fence is 64 bytes.
So why wouldn't the fence catch that particular case?
Because I by design, I jumped over the fence. Then, look, I did A of I, okay, B minus A of I.
Yeah.
Okay, point arithmetic guarantees that this is equal to B of 0. Why? Because A of B minus A is equal to what? Is equal to the address of A plus B minus A, and which is equal to B.
Okay.
Star. Star. So I jumped over. I jumped right there. Okay, if I had made that A of -1, it would have. Well, let's try what it would have done. So we would have gotten an invalid write of size 4 bytes before a block of size 40 allocated in here. Okay, and also notice that in this case, this allocation get array was done on line 30. Okay, so if you look at line 30, in fact, that is where B was allocated, right? So this access would go 4 bytes before the B. Okay, so there are some things that many overflow errors that Valgrind just flags, and they're really easy to see, and you just see them, fix them, and you move on. But some Valgrind does not, especially if you're using one pointer, and your pointer arithmetic is so far off that you happen to fall into some validly allocated area. And there must be at least fence wide. I'll show you that Valgrind indeed tracks things at bit granularity. And to show you this, consider this simple code here. So I'm allocating a new int on the heap, and I'm setting the least significant bit on that int on the heap. And then I'm testing it. I'm testing if it's set. If it's set, I say yes, otherwise I say no. Then I am testing the next least significant bit. Let's see if that's set or not. And so if I run this, it will tell me in fact that conditional jumper move depends on uninitialized value, line 46. Line 46 is this test here, but not this test. Okay, so it says this conditional, the compiler will have turned this into conditional jump branch here, and this depends on the uninitialized value, right, because I only initialized the least significant bit in that particular 32-bit. Right, so this is what Valgrind does. Any